Welcome to San Francisco and welcome to Build 2015. And welcome developers. And of course, you're all developers and you all have apps. And what do you want for your apps? Well, you want more users. And as we heard this morning, the best way to get more users, to get those billions of users, is with universal apps for Windows. Some of you already have apps. Actually, all of you probably already have apps, either for desktop on Win32 or .NET, on Windows and for the Windows Store on Windows 8 and 8.1, for Windows Phone, or even for iOS and Android. But for all of you to get to the Universal Windows platform, we'll go through today kind of all the things that you need to know for your app to be a good citizen and to behave properly as a universal Windows app. So my name is Sean Henry. I'm a program manager on the Windows Developer Ecosystem Platform team, and we're here today to talk about the Windows application lifecycle. So a couple bookkeeping things first. Be sure to rate all your sessions. You can rate mine based on the first slide if you want, but you'll get another opportunity a little bit later to rate them as well at the end of the session. I don't know why I had to do this one now. Just kind of a you are here. So this is the app model track for Windows. A lot of you probably came before lunch from Andrew's session. I hope you rated that well because he's buying supper tonight and I want him to be in a good mood. But we're here in the session at the bottom, which is the kernel, how Windows really talks to your app and how it interacts with your app and how it sends you messages. And kind of what do we mean by that? Well, by the events and the messages we send to Windows, we mean things like suspension and resume of your events, how and when your application can execute in the background, how we give it access to resources like memory and CPU so that it can most efficiently use the battery on battery-powered devices. And then, of course, just system triggers like timer events and events that happen within the system, like push notifications and how those get triggered into your app in the background. And of course, the good news is that we've built this into the Universal Windows platform. So we built something that scales all the way from our phone and IoT devices all the way up through tablets and desktops into really powerful desktops and Xbox machines and the Surface Hub and the HoloLens. And the good news for you guys is that you get to write the same code and it runs absolutely everywhere. But there are some differences with how sort of apps behave, obviously, as we scale across these different devices that have different amounts of memory and different amounts of CPU and so on. So before I get started here on the foreground application lifecycle, quick show of hands. How many of you are Win32.NET desktop developers? So a lot, so like over half it looks like. How many of you are Windows Store developers? Also half. And Windows Phone developers? So 3 halves, perfect. So I know a lot of you probably have apps for multiple platforms, and of course that's why we're here, is because it's going to save you a whole bunch of time to be able to build one app across all the places that Windows is. And if you're already building Windows Store applications or Windows Phone applications, there's not going to be that much work for you to do. You're already familiar with the basics of the application lifecycle. If you're coming from Win32 or .NET, there's some more things that you'll have to learn in order to behave really well as a universal Windows app. So we'll start off with the foreground application lifecycle and with the basics of application lifetime. So your app can be really in one of 3 states: not running, running, or suspended. So not running is kind of obvious. Your app is not running. The user's not using it. It's just sitting there on disk. And if the user launches it, it's considered an activation event. This would be them tapping on a tile. And the app will come up, and it now enters the running state. And they're using your app, they're pressing buttons, they're scrolling around, they're tapping things. And the app is running, and it's in the foreground. As your app moves to the background, and this can mean different things on different SKUs, but for instance on the phone, if they hit the start button and move to another app, that's considered your app moving backwards, moving to the background. The OS will then suspend your application. So at this point, it's still sitting in memory, but all of its threads, all of its execution is suspended, so it's not running. It's just sitting there completely suspended in the background. If the user goes back into your app, you'll get a resuming event, and it'll keep running again. If at some point Windows needs the memory that your app is using for something else. So if there's another app that's coming in, for instance, that the user wants to use and it needs that memory, we'll move your app back into the non-running state. So we'll take it out of memory. And you'll see here you get events as you transition between all of these states: an activated event, a suspending event, and a resuming event. And, but you see there's no event between suspended and not running. So when you move to the suspended event, you have to assume you may never come back out of that event. You may go to not running. So you have to completely serialize any state you have in order to be able to resume back into that event. So this is kind of a little bit more states than sort of a Win32 or .NET would have, which really you could think of. We didn't really think of them as having these lifetime states, but really they had not running and running. Didn't have this kind of suspended state in the middle. And of course, for universal Windows applications and all modern applications, apps are typically in that suspended state, and then and reside there and we try and keep them there as much as possible, because that's the kind of most efficient state for the battery and for the performance of the machine. So what does this look like in terms of lifetime? So this is kind of a chart I have here that shows time horizontally and then kind of the usage of memory and CPU vertically. So when the user taps in your app, you load some data, you're consuming memory, and then you kind of level off, and the user is using your app and it's running. And at some point, you'll get a suspended message, if they hit the Windows key, if they minimize your app, or so on. At that point, we give you a small window of time to serialize all your data and to get into that suspended state. So there you'll save whatever data is in the form they're looking at, or any data that's in the UI, whatever you need to do to sort of build a state that you can then reconstitute back into when your app is resumed. And of course, at this point, all your threads and your execution is completely suspended as well. So after you finish that suspending state and move into the suspending event, move into the suspended state, your app is not using any CPU at all, with the exception of the background execution stuff that I'll talk about a little bit later. But generally, your application is not using any CPU at all. Of course, it can move back into the running state. We call this a resumed event. You saw that earlier on that diagram. Continue to run. And then if at some point it's in the suspended state and Windows needs the memory for another app to come in, we will then move it to the not running state, so it then gets taken out of memory. But you don't get the opportunity to run again between being suspended and moved into the not running state. So I'll show you this very briefly in code here. I'll move over to a very simple demo I have over here. So this is, everyone can see that all right. So this is a very simple project, very close to sort of the template that you would get if you did a new universal Windows application in Visual Studio. And I've hooked up here to the suspending and resuming events. And so I have handlers for those down here. And we'll just walk through very quickly what happens when I launch this application. So here it is launching. So the first event it gets is this launched event, which maps to the activated event that I was talking about earlier. And this is sort of the first launch of the app. It's never been run before, so we do a full startup from here. And now it's sitting and it's running. So this is a little chat application I've written. And so what you'll see is, while I'm attached to the debugger, actually none of the events will fire. So I've just minimized it there, but it's still actually running in the background. So an important thing to do when you're testing these things when you're developing a Visual Studio is to use this Lifecycle events button here. And you can see I can trigger the various states in the application lifecycle state machine. So I can ask the app to suspend, to resume, or to suspend and then move to a shutdown. So that's moving to the suspended state and then to the not running state. So I'll show you what happens here when I hit suspend. My suspend event fires. And then what's going on in here is I'm saving all my local data. So I have another method here that saves all my data to my isolated storage. And you'll notice here that this is an asynchronous method. So it's important that I grab the suspending operation deferral. And what the deferral does is it says don't don't suspend the app until I call complete on this deferral. If I hadn't done this, what would happen is the save local data would have built a Lambda and spun off on a different thread to save my data, which is great because then it's not on the UI thread and it's happening in the background. But the UI thread would finish, and Windows would then think your app was done executing and would move us into the suspended state. So I grabbed the deferral here, and that tells Windows to keep the app around until I say it's complete. Now, you still don't get to run forever, so when I call suspending here, and so I have a little toast that comes up saying the app is suspending, and then I get, and it depends a little bit between mobile and Windows and our different SKUs what the number is, but typically it's around 5 seconds that you'll get to save all your data and do whatever you need to do in the background. So that's interesting. And I'll just, actually, before I do more code, I'll just show you what happens when I do resume. Sorry, I shouldn't have done that. So I get the resume event, and then, of course, I read all my data back, and here I'm showing a toast. That's resuming. So that's my app moving between the suspended and the resuming state, and using Visual Studio to sort of force those events to happen. Now, what I'm going to do here is I'm going to now try and save some data to the cloud, which takes a little bit longer. And I'm going to do this not in the debugger, just to show you guys what happens. So I'm starting the app here without the debugger. And as that comes up, so it's the same app, and I'll just hit minimized here. And so the app is now moving into the suspending state. Now, the breakpoint didn't get hit because I don't have the debugger attached. But what's happening, you'll notice that toast is not coming up saying I'm suspended. And that's because my app is sitting in this saving cloud data state and is never actually entering the suspended state. And eventually, I don't know if you guys noticed down here, but the icon disappeared. So what happened, we can go to the logs here, and we can see the top log here that Windows thinks my application hung. That was because I spent too long in that resuming method. And Windows made the call that they thought the application was taking too long and that we needed to terminate it so that we could bring the next app in or do whatever that is the user needed. And of course, we do this to sort of keep performance really, really good for universal Windows applications, so that the next app can launch really quickly, so we don't have too much contention between an app running in the background trying to shut down and another app coming in. But what if we needed that extra time? So what if we needed that extra time to save data to the cloud? And you saw there in that particular case, I mean, I'm on a reasonably powerful laptop here. There's not that much going on in the machine. There really is no reason why we couldn't let the app run a little bit longer. So what we've introduced in Windows 10 for universal apps is its concept of extended execution. And what this is it allows your application to ask for more time to not be suspended. So if we sort of use the same diagram as before, and we look at this, we see our app is in the running state, and it gets a suspending event. At this point, we can request an extended execution session. I'll show you this in code in a second. And what this does is it asks Windows, says, hey, if there's resources available, just let me keep running for a little bit longer. And of course, if there are resources available, we'll let you do that. So you'll stay, in this case here, you'll stay in that suspending state. And you can keep saving data or uploading data or whatever you need to do. And then when you're done, you'll enter the suspended state. If Windows needs the resource for something else, if the app that's coming in, the next thing the user is trying to do, needs a lot of memory and we're on a memory-constrained device, or if you're taking a very long time and the battery gets low or gets to a state where we need to sort of conserve it, we'll send you a revoked message. And at that point, you need to clean up very quickly. You only get about a second to clean up. So I'll show you this here quickly in code. So this is the same app here, and I'm in my onSuspending method. So I'm going to take this code here, and I'm just going to replace it with this extended execution session. So what have I done here? So I've created a new extended execution session right here, and I've supplied a couple parameters. So I've said the reason is I'm saving data, and you'll see in the current builds of the SDK, there's only a few reasons: location tracking, which I'll go over in a second, saving data, and unspecified. This is something we'll extend in the future, but in the current builds, these are the only 3 options you have, and you must supply a reason, and then as well as a description, which are things that will show up in the UI to tell the user what's going on in the background if they need to figure out why an app's still running or why things are going on in the background. So I enter the description and the reason, hook up to the revoke event, which I mentioned earlier. So I've hooked it up here. If that revoke gets called, then I'll close my connection really quickly and kind of get out of the way. Then the first thing I do is I save my local data. I know that this doesn't take very much time, so I'm just going to do that anyways. And I know I can get that done in the time that Windows gives me. If I have my extended execution if I get an allowed back, so I can potentially get allowed or I can get denied, if there's no resources available at the start, we won't even give you the session to begin with. But typically you'll get an allowed. And at this point, I'll start saving my cloud data. So we can see, this is the same app here. And we can see it continuing to run if I minimize here, if I call the suspend operator, the suspend button. I'll move through all this. And then I save my data, and I check that my result here is allowed. And now I start saving my data to the cloud. And so this will take a few seconds because my data takes a long time to go to the cloud. Maybe I'm on a slow connection or something like that. And it's just churning around, sending my data to the cloud in the background, and then it'll send a toast notification when we're done. Unless I'm hitting a bug where it's not, and it'll show up in here in a second. Yeah, so maybe that toast didn't come through. But anyways, you have to trust me that toast would come through, and you would get a toast notification. Your session would complete, and then you'd move into the suspending state. So that's extended execution. That's kind of one half of extended execution. The other option is to call extended execution at some point while your app is running in the foreground, not during the suspended method. Suspended callback event. And of course, this could be if you know ahead of time that you're going to want to continue running in the background. So, an example using the reasons that we have that I showed you before is background location tracking. So if you have a turn-by-turn navigation application or a fitness application that wants to track the user's location in the background, whenever you start that session, when you click turn by turn, or start your run or your bike ride or whatever it is for your app, you can request your extension then, and in that case, your app won't even get the suspended event. You can listen to the core window if you want to understand when your app is in the foreground or not, and you can listen to the memory manager events to tell you if the amount of memory your app is allowed to use changes, if your memory caps change. But you won't get that suspended event. You'll just keep running in the background, and again, if Windows needs the resources for something else, we'll send you the revoked event, and your app will have to clean up. And typically, of course, if we send you revoked, it's because we need the resources for something. We're not just going to enter the suspension. In this case, we'll actually do a suspend and then terminate. So I'll show you really quickly what that looks like. I actually have here kind of neat the actual Maps application. This is the Maps app that ships. Again, it's a universal Windows app, so the same app ships on Windows and Windows Phone and all Windows devices that have maps. And it looks like my Wi-Fi is a little slow here. Looks like the maps aren't coming down. Anyways, so I can ask Maps for directions, and so I can say, well, I want to go back to my hotel here, and so it's giving me directions. It's giving me driving directions. Oh, I got to switch over? Is that what's going on? All right. So this is the real Maps app here, and I think my connection's a little slow, so I'm not getting the full maps coming in, but it's got the streets data and looks like the traffic data, which is probably all I need. So I've just asked it to take me from my location to my hotel. I'm going to do walking directions since that seems a little bit quicker. And then when I click go, here now the Maps app has entered its extended execution session. And it's doing exactly the same thing here, except this is not actually in a suspended event. This is just when I've started the navigation session. Doing the same thing, I'm creating an extended execution session. I'm giving a reason of location tracking, checking the result, and if it's allowed, I then start my navigation session. In this case here, they're subscribing to the events off of core window so that they know if they're in the foreground or not. So now also the maps came in now. And so now it's giving me my turn-by-turn directions, and of course I can minimize this, and it will still give me my directions. So those are kind of the two ways that you can use extended execution. And of course, as I mentioned, this will vary a little bit based on devices, on how much memory they have, sort of how much time you'll get. It's not guaranteed, it's an opportunistic thing. On desktops with lots of memory, you'll be able to run pretty much unconstrained in the background. On some of the phone devices and IoT devices where there's very, very little memory and there's typically only enough memory to keep one or two apps active at a time, you'll find that the amount of time that you can run in this state is often much shorter. So that's kind of the big new piece that we have for foreground execution in Windows 10. I'm going to move over now to background execution. And when I talk about background execution, what I mean here is really just ways that your app can come alive in the background and sort of draw your user back in, either by responding to push notifications or events in the system events in the background to update your tile, or things like tracking location, using geofences, or playing music in the background, or connecting to Bluetooth devices. So these are really cases where your app isn't running, but it's responding to things happening on the device and to system events. And background execution in general has kind of had a long story on both Windows and Windows Phone. And the good news is, again, here we've completely converged on all Windows SKUs, both desktop and Windows Phone, and all the Windows 10 SKUs. So if a lot of you are Windows Phone developers, and coming from Windows Phone, you may remember background agents, which are things that would fire periodically. Agents that would fire every 30 minutes or so. You could update your tile. And then if you're coming from Windows 8, you're familiar with the concept of background tasks and triggers. We added those in Windows Phone 8.1. So we had kind of a converged background model on Windows 8, between Windows 8.1 and Windows Phone 8.1 if you were building Windows Store applications, as well as Silverlight 8.1 applications could also use the converged background task model. Then of course in Windows 10, everyone's big happy family, all of the Windows SKUs all use the same background execution model. So for those of you coming from Win32 or .NET, where you're not really familiar with this concept of having a separate model for running in the background, the way we define background execution on Windows, the universal Windows platform, is with triggers and background tasks. So background task is kind of the unit, the module that actually runs in the background, the code that runs in the background. And the trigger is the thing that causes that module to start running, that code to start running. And apps subscribe to triggers, and when those triggers fire, their code start running. So for example, you can subscribe to a push notification trigger. Your background task will fire when a push notification comes in. Geofencing as well. If your device moves locations, it can cross a geofence, which is get within a particular radius of some location, and you can have a trigger fire in those cases. Obviously, Bluetooth as well. With bands and all sorts of devices, watches and smartwatches and so on, we send notifications via Bluetooth, and your apps can subscribe to things like that, heart rate monitors and so on, that are all Bluetooth devices. Regular timer events or system events, just things happening on the system, periodic timers again, Wi-Fi becoming available, users logging in, that kind of stuff you can subscribe to. And then of course app services. There's a whole session on app services and app-to-app communication a little bit later in the week, but those are also backed by background tasks. And those are kind of interesting because that's a case where you can actually, your app can call another app's background service, a background task to do work on your behalf. So it allows kind of this web of apps to call other apps to get information and have work done for them. So just an introduction, I'll give a really quick demo here on the basics of background tasks and a couple things that have changed as we converged our background execution model across Windows, across all the Windows SKUs. So this is again a very simple app, my same simple chat application. And what I've done here is when this page loads, I'm going to register a bunch of background tasks. So the first thing that I need to do is request access to run in the background. Let me minimize this so you guys can see it. And so I'm calling here the background execution manager and calling request access. And what this does is it asks Windows to give this app permission to run in the background. Your app has to do this if it wants to run in the background. If it doesn't do this, none of the triggers that you register will fire. If you're coming from Windows store development on Windows 8 and Windows 8.1, calling this API would bring up some Windows UI that would ask the user to pin their app to the lock screen. For universal Windows apps, we don't do that, so that's kind of an important distinction. It's more similar to the Windows Phone model, where your app will just typically be granted access anyways. Cases where you wouldn't be granted access is if the user has explicitly disallowed your app from running in the background. So we have battery saver across all Windows desktop and Windows mobile now, so the user could go into battery saver or into the background task control panel and prevent your app from running in the background if they don't want your app to be consuming battery or doing stuff in the background. So that would be a case where you would get denied. So you should always request access. There's also a get on here that you can call if you ever want to check if the user has changed the state of whether you can run in the background. Yeah, so there's a get access as well that you can call. You can see it right there. So that's requesting to run in the background. Also, best practice is to unregister any tasks that you have. So I'm just going to check if there's a timer task already registered, and I'm going to unregister it here. So I'm enumerating all the tasks here and then unregistering them. And then finally, I'm going to register my task here. So in this case here, I've created a timer trigger. I'll fix that in a second. So I've created a timer trigger. The parameters this takes, it takes a timeout of time interval of 15 minutes. And then one shot means do I want this to reoccur or not. So setting this to false means I want the timer to reoccur every 15 minutes. I create this thing called the background task builder, which helps me build these task instances. Give it a name, an entry point. So I've already added to this solution here a WinRT component that has my background task in it. So I'll show you that in a second. But so I specify that as my entry point, my timer task here. I set the trigger. I can also set conditions. So I could, for instance, also add a condition to here. And what conditions kind of work with triggers as something else that must happen in order for that trigger to fire. So I can add, say, a system condition. Here we go. A system condition type of, say, internet available. And in that case, this, new system condition. I'll just skip that. But anyways, you can add a system condition of that will be something that will also have to be true for that task to fire. So in that case, I can add a system condition, and if the internet weren't available, my time trigger wouldn't fire. What would happen is after the 15-minute interval, my timer would latch, which would mean it's ready to fire, and then as soon as the internet became available, the trigger would fire and my background task would run. So if I checked here for the registration, here I can then get the name. So now I register my task. So I can run this, and we can all wait around for 15 minutes for this trigger to fire. No, just kidding. We're not going to wait for that to happen. Again, handy Visual Studio will give us in the lifecycle events for background tasks. Oh, here's the registration breakpoint. In the lifecycle events for background tasks, our lifecycle events menu, we can see our list of background tasks here, and so I can, in this case, explicitly fire the timer task. If I had to put a breakpoint on there, that would hit the run method, and that just popped a toast. So I'll do that again so we can look at the actual task here. So I told you before that this task was a WinRT component that I added to this solution. It implements iBackgroundTask, and kind of the only interesting thing that iBackgroundTask has is this run method. And the run method is what gets called when your trigger fires. So you can see here when I force that task to fire via Visual Studio, my run method was called. I'm hooking up here to the cancel method. This is what Windows will call if you run out of time to run your background task. And so I can handle that down below, and then I show a toast. And so that's just showing a toast down here in this code. And then one more thing you have to do to finish registering your background task. Well, two more things. One is you have to reference it from your foreground project, but then also you have to add an entry in your manifest. So here we see extensions element being added. There's also a wizard for this in the designer that makes this a fair bit simpler. But this shows you exactly what's going on. I've created a background task here, and I've specified the entry point to be in my background task assembly in the timer task class. And then I've said that my task type is timer. And then here you can specify all sorts of different task types as well. So that's the basics of background tasks. We have a bunch of triggers. If you've been familiar from Windows 8.1, we had system triggers, time triggers, maintenance triggers. Those have been around for a while. In Windows Phone 8.1, we added a bunch of new triggers. Cached file, which is for grabbing data from the cloud for file pickers. A couple Bluetooth triggers, device connection trigger, GAT and RF COM are all for Bluetooth. And then the location trigger, which is for geofencing. And then in Windows 10, we've added a ton more triggers. So we've almost doubled the number of triggers that we have. We've added a few triggers for accessing the data store of appointments and contacts on the device. More Bluetooth triggers for Bluetooth LE, as well as Device Watcher, which is a new type of Bluetooth trigger that can listen for advertisements from Bluetooth devices. Two sensor triggers, activity sensor trigger, and sensor data threshold trigger, which can be used for things like pedometers or listening to the accelerometer, that kind of stuff. A couple triggers for toast notifications. So if the user taps on or works with your toast notification, your actionable toast notifications, or notifications in the action center, those will fire a trigger which can activate a background task, and then you can do some work. And then the application trigger and socket activity trigger, I won't ruin the surprise for those. I'll talk about those in a second. But all the ones above that, there are sessions later on I'll point you to at the end of the deck where folks talk about those triggers. So those are all the new triggers that we've added in Windows 10. We've also, and those are available, of course, on all Windows, on Windows Desktop and Windows Phone, Windows Mobile, as long as obviously the device supports those particular things. If the device doesn't have a GPS, then obviously the location trigger is not going to fire. So more good news, we've converged resource management of background tasks across Windows, across all Windows devices. If you remember, if you're coming from Windows 8.1, there was this concept of CPU time and a pool of CPU resources that your app would have access to in the background. If you used up those resources, it would have to wait for that CPU pool to refill. We've simplified things a little bit here and separated for default background tasks. It will look very similar to the model, again, we had on Windows Phone for Windows Phone 8.1. So you have a memory cap, and this is for 512 meg devices here. This scales up as we move up to more devices with more memory. But on kind of our 512 meg devices, which are some of our devices with the least amount of memory, your your background task will get 16 megabytes of memory to run, and will run for 30 seconds. Something just happened. There we go. 30 seconds in the background. After 25 seconds of running, we'll send a cancel notification to your task. So you will get some warning that your time is about to run out. So you get 25 plus 5 seconds to run. And you get at least 10% of CPU, so that's kind of a soft cap. If there's nothing else going on the device, you can use as much CPU as available, but you're guaranteed to get that 10%. And of course, tasks can be blocked if the users block them in Battery Saver or in the background task control panel. The other set is long-running or opportunistic background tasks. Those typically have the same memory caps, but they can run for as long as there are resources available, so not just for 30 seconds. Excuse me. They can run much, much longer if there's resources available on the device. So the triggers that are considered opportunistic triggers are the application trigger, which I'll talk about in a second, the maintenance trigger, which is a trigger that fires when Wi-Fi is available, when the device is plugged in and when it's in a good battery state. Sorry, not when Wi-Fi is available. That was an old condition. Forget I said that. And the device use trigger, which is used for connecting to devices in the background. So that's kind of resource management for background tasks. Sort of related to resource management and background tasks. This is kind of a complex feature, but it's important to talk about it, is that we've added the ability to host background tasks in process with your foreground. So what does this mean? Well, typically on the left here is how background task works. It's hosted in a completely separate process from your application. So your application can be running and your background task can be running, and they're in two separate processes, and they never really talk to each other, and their lifetime is not intertwined in any way. But what you can do now in Windows 10 is you can specify for your background task to be hosted in the foreground process. So they'll both sit in the same process in that case. And the advantage of that is if you want to do inter-process communication between the foreground and the background, well, it's not inter-process communication at that point. It's just communication between those two modules. So that becomes much, much simpler if you have rich communication that you want to do between your background task and your foreground. So this can be useful, again, for those kind of more long-running tasks where you might have them running at the same time as your foreground. The disadvantage, of course, is now you have to keep your whole foreground application around in memory, and especially on devices with a limited amount of memory, that it very, very much increases the chance of your application to not stay resident and in the suspended state. So that's kind of the basics of the background execution model and the convergence that we've made on Windows 10 for universal Windows applications. I want to sort of finish off. I want to talk about two triggers specifically that are new in Windows 10 that I want to show you a quick demo of for both of those. So one is the application trigger. And why do we call this the application trigger? It's because it's triggered by your application. So we're being a little bit clever with the name. Basically, what happens in this case, instead of waiting for like a timer to go off or for Wi-Fi to become available or whatever, you actually explicitly fire it from your application. And so this is really useful if your app needs to sync a bunch of data at the beginning, like if you're syncing a bunch of contacts or data from like a news feed or something at the beginning, and the user may launch your app, check something real quick, and then navigate away. Previously, your app wouldn't have time to sync data. The application trigger allows you to do that. And of course, it's more efficient than using something like extended execution, because if you host in a separate process, you're only using that small amount of memory, and you're much more likely to be able to keep running for much longer. So I'll show you a quick demo of that. So the registration of this is almost exactly the same as before for the basic background tasks. So here I'm requesting access async and so on. The difference here, I'm creating an application trigger. And after I register it, I do two things. One is I create a value set, and this is basically a dictionary that I pass to the background task, so it has information to know what it's supposed to do. There's a very simple, lightweight way of passing information between your foreground and your background. So I've just put a couple strings in here, but you can put anything that's serializable in this, serializable to a string into this value set. And then here's where the magic happens here. On the trigger, I actually call request on it. And so this asks the trigger to fire right away. And I can get different results. Either it was allowed, it was already running, or for whatever reason it's been disabled from running. So if the user's disabled your background tasks. And if it's allowed, I'm showing syncing progress in the background. But then I'll show you here what's happening in the background task. Again, very much exactly the same as the as any background task. So as soon as this app comes up, the first page is going to kick off this background task to start syncing data in the background. So you can see I register, and then my task immediately gets called to run. I didn't have to do anything in this case because I explicitly called it from my foreground app. And so you see hello here, and it's going to start syncing data and sending some toast notifications, hopefully. There we go. So those aren't popping up like before, but they're showing up at least in Action Center here. And if I kill this app, my syncing still continues in the background. There's 30%, there's 40%. So my background task right now is continuing to run in the background and sync data, even while my foreground app isn't running. So that's, again, particularly useful for these kind of initial sync operations, these long-running sync operations. One other trigger I want to talk about is the socket trigger. This is a really powerful new trigger that we've added in Windows 10, which allows app to have their network connectivity maintained even when they're no longer running. So again, if you're coming from Windows Store applications, you may be familiar with the control channel trigger. It was a little bit more obscure, but this was basically a trigger that would allow you to keep a background task suspended in memory, sitting on a network socket, and then waking that task up whenever there was data coming in on that network socket. The disadvantage of that was, of course, your app had to stick around in memory. So it didn't work very well on devices where there was a limited amount of memory. So the big improvement with socket trigger tasks is that we actually now broker that socket and hold on to it for you in the operating system. And so that means your task can completely go away and completely be removed from memory, and we will wake you up and reactivate you whenever there's data on that socket. So this is a good alternative to using WNS. If you have your own push notification system, if you have your own server infrastructure for sending push notifications, half of the room is probably thinking, why would I ever want to do that? And the other half is like, that sounds great, I absolutely have that and I want to do that. But yeah, so if you have that situation where you have your own sort of push notification system, this will really be helpful there. So the way this kind of works is you create your socket in the foreground and you register your background task, and then you hand off your socket between the foreground and the background. So if you're using your socket in the foreground, you grab the socket from the socket broker, you use it, do whatever you need to do, and then you hand it back to the broker, and then your app goes away and then gets reactivated if there's data on that socket. So I'll show you this quickly here in a demo. So I'm just going to kick off here really briefly. I have a little server program that is just like a little telnet server that runs, and then a little bot that sends messages to it. So these are just Win32 or .NET applications, console applications. And then here is the UWP application. So I'll just run through this real quick here. So again, here I'm registering the task. Same as before, same pattern as before. In this case, I'm using a socket activity trigger. So this is this socket trigger. And if my socket trigger is successfully registered, I then go and I connect my socket in the background. So Here I'm just using a stream socket, and I'm connecting to localhost. That's that server that I showed you there, that little telnet server. And on the socket, on the stream socket itself, there's this new method called enable transfer ownership. I give it an ID that I can make up whatever string I want, and I say I want it to wake up in connected standby. And then I say I'm done with it. So I'm going to transfer the ownership back to the socket broker with the name here, and then this time span here is how often I want the keep alive to be. And we'll try and honor as low a keep alive as possible. So here I've connected, and then what you'll see in a second is, so that bot woke up, and what's happening with the bot is he's sending a message every 5 seconds or so. So what happened is I connected to that server, and then I handed the socket back to the broker, and then my chatbot here then sent a message to the server, which then relayed it back to my app, which then activated my background task. So my app could have been completely gone, completely terminated, not in memory, and my background task would have been activated here in the run method. And so in my run method, I grab the trigger details, which gives me information about the socket, and I can retrieve the socket from there, which is what I'm doing here. I check the reason. I say that it was because of socket activity, which is great. That means there was data on the socket that I want to process. And then I read that data, and then I show a toast here. So I got a bunch of these that I'm just going to clear here. But again, my app could be completely gone, and I would still get toast notifications coming in, and my background task would be activated, even when I'm not running anymore. So that's a very powerful new trigger for network-based applications that want to listen to data coming in the background. So that's kind of the main stuff I wanted to show you today. Just to wrap things up, great news for everything is that the application lifecycle and background execution is completely converged across Windows, across all the Windows 10 SKUs for Universal Windows apps. So what that means is that you can write the same code and have it run on all Windows devices. The thing, of course, you have to be aware of is that despite all the new things that you can do, all the tons of new triggers and capabilities that we've added, resources are still limited especially on our mobile devices and the IoT devices. So you have to be aware of what happens when there's low memory or when the device is on battery, and we need to sort of conserve resources in that case. So that's when you'll get these notifications from Windows about what your app is doing. So there's a few other sessions that you really should go to. So there's a couple session on Thursday that will talk a lot about some of those new contacts and appointments triggers. A session on Friday around the new Bluetooth triggers. And then I talked a lot here about how Windows talks to your app. Robert has a session on Friday around what your app should do in those cases and how it should handle those kind of handle windowing events and so on internally. The new toast notification triggers will be covered in a session on Friday with Thomas. And then app services, which is a great new feature that you probably heard a lot about in Andrew's session. Arun has a session. Arun and Sandeep have a session on that on Friday. So if there's any questions, you can ask them to me now. You can meet me in the Insiders Lounge, or you can reach out to me on Twitter. I am @SeanHenry. And one more chance to evaluate this session. Great. Thanks, everyone.